All right, today we're going to tackle a really cool puzzle. One that affects pretty much every delivery driver, city planner, and yeah, even the original postman. It's called the Chinese postman problem. And by the end of this, you'll know exactly how to solve it.
Really think about it for a second. If you had to deliver mail to an entire neighborhood, how would you plan your route to walk the absolute minimum distance while still making sure you hit every single house on every single street? That's the puzzle we're going to solve together.
Now, this puzzle has a few ground rules. You've got to cover every single street at least once, you want your total journey to be as short as humanly possible, and you have to end up right back where you started your day. Efficiency is the name of the game here.
And you might think this is just some modern problem for a GPS to solve, but no way. This was formally laid out way back in 1962 by the Chinese mathematician Quan Meiko. And honestly, its solution is more important today than ever, powering logistics and city planning all over the world.
Okay, so here's our game plan. First, we'll break down the problem and see how you turn a regular map into something we can actually solve. Then we'll crack the code by understanding the why behind it. After that, we'll walk through a 7-step solution with a super clear example, and finally, we'll look at how this whole idea goes way beyond just delivering mail.
So, first things first, how do you take a real-world, kind of messy neighborhood and turn it into something you can solve with math? Well, the answer comes from a concept called a graph, which is really just a fancy way of saying a simplified map of dots and lines.
In this world of graphs, intersections become simple dots we call vertices, and the streets that connect them become lines called edges. The absolute perfect route, the dream scenario, is one where you can trace every single edge without having to retrace your steps. You might have heard of this as an Eulerian trail. The basic idea is you can draw the whole map without ever lifting your pen from the paper.
Now here's the secret. The key to finding that perfect route isn't actually in the streets themselves, but in the intersections. More specifically, it's all about counting how many streets connect to each one.
Let's look at 2 examples here. On the left, if you count the lines coming out of each dot, you'll see that every single intersection connects to 3 streets. That's an odd number. And think about it. If you arrive at an intersection through one street, you need a different street to leave. An odd number of streets means you're going to get stuck eventually. Now, look at the graph on the right. This one's a little better. Only 2 intersections, A and D, have an odd number of streets. So here's the bottom line, the really crucial point. If your map has more than 2 intersections with an odd number of streets, it is impossible to find a route that doesn't rewalk some paths. If it has exactly 2, you can do it, but you have to start at one of the odd spots and you'll end at the other one, which, breaks our postman's rule of ending up back home. But now, check this out. On the left, we've got that map with just 2 odd vertices. It's close, but not perfect. Now look at the graph on the right. Go ahead, pick any dot and count the lines coming off of it. You'll find that every single one of them has an even number of connections. This is our perfect scenario.
And this right here is our ultimate mission. To solve the Chinese postman problem, we have to cleverly modify our map. We have to figure out which paths to retrace, which streets to walk down twice, to turn every single odd vertex into an even one. That's what creates a perfect route and lets our postman start and end at the same spot as efficiently as possible.
So how do we do it? How do we turn an imperfect map into a perfect one? Well, thankfully, there's a mathematical recipe for that. Let's walk through the 7-step algorithm that can turn any neighborhood map into the most efficient route possible. Here it is, our 7-step plan. I know it might look a little intimidating on paper, but trust me, the logic is super straightforward. Steps 1 and 2 are all about finding the problem spots, our odd intersections. 3 and 4 are about finding the cheapest, quickest way to fix them. And the last few steps are just about applying that fix to our map and figuring out the final best route. Let's see it in action. All right, theory is great and all, but let's make this real. We're going to take this sample map right here and use our 7-step algorithm to find the single best route from start to finish. Step 1 is super simple. We just go through our map and count the number of streets connected to each intersection. Let's see. C has 1, 2, 3, 4 streets. That's even, so it's not a problem. But if we check A, B, D, and E, yep, each one has 3 streets connecting to it. Bingo. Those are our 4 problem spots, our odd vertices. Okay, for step 2, we just need to list all the possible ways we can match up these 4 odd vertices into pairs. So we could pair A with B and D with E. That's one option. Or we could pair A with D and B with E. Or our final option, A with E and B with D. These are the 3 different ways we could try to fix our map.
Now we get to do a little bit of math. The numbers you see on the map represent the distance of each street. So for our first pairing, we need the shortest path between A and B, which has a distance of 8. The shortest path between D and E is also 8. So the total extra walk for this option is 8 plus 8, which is 16.
Now let's check out our second pairing. The shortest path between A and D is 6 units. Then the shortest path between B and E is also 6. You add those together and the total extra distance for this option is 12. Ooh, okay, much better than 16. And this bar chart just makes the best choice crystal clear, doesn't it? We did the math for the third option, pairing A with E and B with D, and now it gives us a total added distance of 20. So, comparing the three, that 12 we got is clearly the winner. It's the most efficient way to solve our odd vertex problem.
So for step 5, we take those winning paths, A to D and B to E, and we basically add them to our map. This just means our postman will have to walk down those streets twice. But look at what happens when we do that. Now every single intersection on the map is even. Our graph is perfect.
Almost there. On to step 6. All we do here is take the sum of all the original street lengths, which was 48, and we add the extra distance we just figured out, which was 12. And that gives us a grand total of 60. This is it, the absolute shortest distance possible to cover every single street. And finally, step 7. With our new, perfectly balanced map, we can trace out the final route. And the path you see here does just that. It starts and ends at A, and it successfully travels along every single street, including those doubled-up paths, for that optimal total length of 60. We solved it. Okay, so that was a lot of fun, but let's zoom out for a second. This algorithm is incredibly powerful, and it's used for so much more than just planning a mail route. Why does all this matter in the real world?
I mean, this kind of logic is literally everywhere. It's what helps snowplows clear every single road without wasting fuel. It lets garbage trucks plan their weekly routes efficiently. Heck, you could use it to plan the perfect sightseeing tour to make sure a tourist sees every landmark, or even your own shopping trip so you don't miss an aisle. It's all about maximum coverage for minimum effort.
So, the next time you're planning any kind of multi-stop trip or even just running errands, remember the postman's puzzle. The most efficient path isn't always the most obvious one. So what journey in your life could you make just a little bit smarter? Thanks for watching.